All right, let's talk about speed, but not the kind you see on a racetrack. We're talking about the speed of chemistry itself, how fast things happen on a molecular level. Welcome to the world of chemical kinetics, the science of speed. Let's get right into it.
You've seen this, right? You leave food out and it goes bad way faster than it does in the fridge. Or think about a campfire. A log will just sit there forever, but touch a match to it and poof, you've got a fire. Some reactions are lightning fast, others are super slow. So what gives? What's the master controller behind the timing of it all?
Well, believe it or not, there's a whole field of science dedicated to answering exactly that. It's called chemical kinetics. It's the study of reaction speed, and it explains everything from why your milk sours to why fireworks explode. It's all about how fast chemical changes happen.
Okay, so if we're going to talk about speed, we need a way to measure it, right? We need a kind of chemical speedometer. Let's dig into how we actually measure a reaction's rate.
The official term for this is the average rate of reaction. Now, that formula might look a little intimidating, but it's actually super simple. That triangle, delta, just means change in. So, rate equals the change in concentration, that's the C, over the change in time, the T. It's just like calculating a car speed in miles per hour, but here we're measuring the change in stuff per second.
Yeah, to put it even more simply, think about baking a cake. You can either measure how fast your ingredients, your reactants, are getting used up from the bowls, or you can measure how fast the cake, your product, is rising in the oven. It's the same process, just two different ways of looking at it.
So, we know how to measure the speed. The next big question is, what controls it? What's pressing the gas pedal or slamming on the brakes for a chemical reaction? Well, the answer to that is found in something called the rate law.
The rate law is basically a formula that tells you exactly how the amount of your starting stuff, your reactants, affects the speed. In this equation, K is a constant, and A and B are just the concentrations of your reactants. Those little X and Y exponents, they're the real magic here, telling us just how important each reactant is to the overall speed.
So, about those magic exponents, X and Y, if you add them up, you get what's called the reaction order. This is a super important number because it tells you how sensitive the reaction is to the amount of stuff you start with. And here's the crucial part. You can't just look at a chemical equation and figure it out. Nope, you have to actually go into the lab and run experiments to find it. It's a purely experimental value.
And this is where people can get tripped up. So let's clear it up. There's order, which we just talked about, and then there's molecularity. They sound similar, but they are totally different. Order, as we said, comes from experiments. You measure it. It can be a whole number, fraction, even zero. Molecularity, on the other hand, is theoretical. It's just a count of how many molecules smash together in a single step of reaction. It has to be a positive whole number. One is what you see in the real world, the other is what you imagine on paper.
Okay, we've been looking at this from a high level, with rates and laws, but let's zoom way in. Let's get down to the molecular level and ask, why do reactions even happen? What actually has to take place for one molecule to become another? This brings us to collision theory, which basically lays out three simple rules. For a reaction to happen, molecules have to do three things. 1, they have to actually collide. Makes sense. 2, they have to collide with enough force, enough energy. And 3, and this one's a bit tricky, they have to hit each other in exactly the right way with the proper orientation. Think of it like a key in a lock. It doesn't matter how hard you shove the key in if it's upside down.
That second rule, having enough energy, is so important it gets its own name, activation energy. You can literally think of it as an energy fee, or the price of admission to the reaction club. If two molecules collide but don't have enough combined energy to pay that fee, they just bounce off each other unchanged. No reaction.
Here's a great way to picture it. Imagine the activation energy is a giant hill. Your starting molecules, the reactants, are at the bottom on one side. The final products are waiting on the other side. To get there, the reactants have to gain enough energy to make it all the way to the top of that hill. And this is what that hill looks like to a chemist. On the left, we have our reactants, just chilling at their starting energy level. For the reaction to happen, they have to absorb energy and climb all the way to the top of that peak. That peak is the activation energy barrier. Once they make it over, they can slide down the other side and become the products.
Okay, so if reactions are all about climbing these energy hills, can we cheat? Can we control the speed? You bet we can. Let's talk about the two main ways we can manipulate reaction rates: temperature and catalysts.
First, let's talk about temperature. This one's pretty intuitive. What happens when you heat something up?
the molecules inside start zipping around like crazy. More speed means more collisions, and crucially, it means the collisions are harder and more energetic. With all that extra energy, a much bigger percentage of molecules will have what it takes to get over that activation hill.
The second tool in our toolbox is a catalyst. Catalysts are amazing. They are like a chemical matchmaker. They jump into a reaction, make it happen way faster, and then pop out at the end completely unchanged, ready to do it all over again. They're not part of the reactants or products, they're just helpers.
So how in the world do they do that? It's not magic. It's actually pretty clever. A catalyst doesn't give the molecules more energy to climb the hill. Instead, it finds a completely different path, a shortcut. It provides a new route from reactants to products that has a much, much lower activation energy. So, it's not helping the molecules climb better, it's just making the hill smaller.
Let's go back to our energy hill diagram. So here's our original path, without any help. See how high that hill is? That's the big energy barrier the molecules have to overcome on their own.
And now, look what happens when we add a catalyst. See that new lower path? The catalyst has essentially built a tunnel right through the mountain. Instead of a huge climb, it's a much easier journey. It's no surprise that way more molecules can make it through this route, which means the whole reaction speeds up dramatically.
And this brings us right back to our first question about the food on the counter. The spoiling of food is just a bunch of chemical reactions. At warmer room temperature, the molecules have more energy, so plenty of them can make it over that activation energy hill. But when you put the food in the fridge, you lower the temperature, you rob them of that energy, and suddenly very few molecules can make the climb. The reaction slows way, way down.
Pretty cool, right? The speed of chemistry is literally everywhere. It's in the way we cook our food, how our bodies digest it, how glue dries, how paint sets. So now that you know the secrets, concentration, temperature, activation energy, and catalysts, start looking around. Where else in your life do you see this science of speed at work? Thanks for tuning in.